Get to go. Hi everyone, and welcome to our SAEON seminar for Feb. Sorry, it's a little bit late, but at least we managed to organize it. So today we have Dr. Wade de Kock, who's going to be chatting about some of his PhD work that he did a while ago. So Wade is currently the SAPRI engagement manager. So we kind of just want to show you guys that he's got some kind of background info and other aspects of SAEON and things that you might find interesting as well. So he's going to be chatting to us a bit about the work he did for his PhD on summer rainfall in the Western Cape. So yeah, over to you, Wade. You're still on mute, Wade.
Sorry about that.
You're good.
Hi, everyone. Welcome to my talk. Like Caitlin mentioned, I'm going to be talking about the summer rain, so the extended summer, so from October through to March, and in the Southwestern Cape, because those of us who live in the Cape know that the Southwestern Cape's rainfall is quite different to the rest of the Western Cape. Caitlin did do an intro for me, but just to add, so during my PhD, I actually worked in the plastics industry. So I worked for the South African Plastics Pact, where I did a lot of data analytics and also engaging with a lot of large companies within South Africa. I then also worked in the waste and circularity space, so improving recyclability in the city of Cape Town as well as Joburg. And a lot of that was working with civil society and government, so looking at getting waste reclaimers or waste pickers to set themselves up as businessmen and women. And then the aim is to basically co-design packaging for circularity. Then I also moved on to the climate change and renewable energy space. So that was working with a lot of policymakers, schools, and communities, because there's all this hype in South Africa around the just transition in South Africa. So for example, having a whole entire value chain of miners and coal workers then moving on to greener energy. And that was quite interesting. So here's a bit of pictures from my experience there. So giving students a platform to advocate for climate change and renewable energy, but also on a more political front, having municipalities such as Namakwa, such as West Coast District, develop their own response plan to climate change. And then obviously we have a lot of exhibits and workshops and had the students design things and attend summits and et cetera, et cetera. So a bit more on the work that my PhD was on. So like I mentioned, the Southwestern Cape, Caitlin, I don't think it's, oh, that was quick. So like I mentioned, the Southwestern Cape is a winter dominant rainfall region. A lot of research has been going into specifically winter rainfall. However, and there's a nice paper by Mahlalela et al. That actually showcases how a negative SAM is also indicative of a wetter rainfall season. So how I actually conducted my research. So I got 27 weather stations from 1979 to 2019 in the Southwestern Cape. And this had at least 95% good data. I then went and I calculated an R value. So I obviously had to rank rainfall systems according to how intense they were. So you don't have to remember the M and the N, but basically the R value is an arbitrary value that accounts for the duration of the rainfall, across how many weather stations that rain actually fell, and then obviously the sheer volume, so the millimeters of rain that actually happened. So we managed to get a top 75 that goes over the 95% threshold. There were a bit more, but they were insignificant in terms of actual rainfall. So there are my 27 weather stations. I then also added the position of the dams according to compared to the actual stations. And what I liked about my research is that I could actually relate science that people wouldn't think is relatable to actual communities in the Southwestern Cape, but it actually is quite relatable. So I then from the top 75, I developed a top 20. So obviously with all that 75 large rainfall events, I then had to identify like from what rain-bearing system they came from. So for a large part, most of them actually were cut-off lows. Second, they were atmospheric rivers. We did find about 3 West Coast troughs, but they weren't as large as the cut-off lows and atmospheric rivers. And I'll explain in a bit what both of those are. But as you can see from the dam before versus the dam after, they contribute quite significantly in terms of dam percentage levels. And this is quite crucial in the summer where the weather is actually the driest and you find the most evaporation. So that can actually compensate for a drier winter. So some characteristics of the large rainfall events, as you can see, so the first A is basically a count of when the top 75 events took place. And you can see that in the last 2 decades, not much has actually happened apart from that one 2013, 2014 season. Then also, if, like I mentioned, looking at the proportion of summer rainfall compared to winter rainfall, you see that in a lot of the cases, it goes above that 30% mark. So the summer rainfall actually accounts for 30% of the entire rain of a whole year. So the red stars actually represent seasons that followed drier than normal winters. So as you can see, for example, October 1998, it follows a drier winter, but the rainfall in the summer is so significant that it actually helps when concerning dam levels. So looking at the rainfall anomalies, again, you can see quite clearly that a lot of the red exists in the last 20 years. And this actually tracks quite nicely with the amount of atmospheric rivers and cut-off lows that actually happened in that season. More noticeably, you can also see that the cut-off lows in gray actually show a decrease in how many times they actually occurred in the season. So how different are cut-off lows and atmospheric rivers? So cut-off lows are characteristically, they have that comma shape of water vapor. And then atmospheric rivers are these narrow plumes of water vapor that actually travel from Amazonia and Central South America down to South Africa. Another difference to note is that cut-off lows generally last a bit longer. So we call them quasi-stationary. So they're quite stationary in some places, but they last for about 3 to 5 days, give or take. And then atmospheric rivers are a bit shorter, but the actual sheer volumes of water that they can actually provide is quite significant. You do get events where one feeds into the other. So for example, you'd have a cut-off low and then it would almost scoop up the moisture and take it with it towards South Africa. And that is a super event, but when classifying, what we considered was that the first rain-bearing system that actually formed, so for example, in this case, it would be the cut-off low, that would be the main characteristic of that system. So looking at the vertical profile, so this is from the University of Wyoming, and the big difference really, apart from the lower inversion layer that the atmospheric river has, so the atmospheric river is from images D to F, is a lot lower. But also what to note for A, B, and C, which is the cut-off low, is the energy at B, that little bit of red is the energy, and it usually exists around 500 hectopascals, which is indicative of a cut-off low. They usually form at that area, whereas atmospheric river is more low-lying, so it's more in the lower troposphere, so around 750, 850. So relating it to dam levels, we'll see in a bit now where Theewaterskloof is, but Theewaterskloof is obviously the largest of the Western Cape's dams. And you can see the atmospheric river fills it up quite nicely. I mean, I did mention that the sheer volume of the water that the atmospheric river produces is quite a bit. And then obviously same goes for Voelvlei and Berg River, which sort of sit in the similar kind of vicinity. So looking at the concentration of events, A is your cutoff lows and B is your atmospheric rivers. So as you can see with A, a lot of the events actually start only existing after the False Bay Peninsula. Whereas with atmospheric rivers, once they actually make land, they tend to start it already starts to rain. And obviously this happens over different time scales as well. So I don't know if you guys can see Theewaterskloof, so that big little blob of blue, that would be where Theewaterskloof sits. And B, being the atmospheric rivers, you see those dots are quite red. So that explains why Theewaterskloof gets such high volumes in terms of atmospheric rivers. So does a R value relate, a high R value relate to dam increases? So the simple answer is probably yes and no. What we do see is that cutoff lows have a different slope than what atmospheric rivers do. So they both influence dam level increases, sure, in a positive way, but they do it differently. So now that we know a bit more about how much rain is actually falling from these events and what it actually does to dam levels, can we compare it to something else in the situation? So looking at extreme hot days, one might think that with more rain falling and more events, that you'd have less extreme hot days, because rain obviously in the Western Cape has a bit of a cooling effect, which is a bit different to the rest of South Africa. And then also wind speed. So I know we've noticed that there's been a noticeable difference in how much the wind has actually picked up over the years. However, this relationship has not been entirely significant compared to the extreme hot days. So can we compare this to the actual rainfall? And like we probably would have guessed, extreme hot days do have a negative relationship with the mean total rainfall. So the more it rains, the cooler it is. And then also with extreme, with wind speeds, you don't quite see that same relationship. So what I did now we're looking at large scale mechanisms. So what other features are actually contributing to whether it rains or whether it doesn't rain in the Southwestern Cape? So what I did was I looked at the 5 hottest seasons and the 5 driest seasons of each of the 40 years. However, as science is, it does get complicated. So what I had to realize is actually I need to strip my entire 6 months. So for example, October, November would be your late spring. December and January would be your core summer. And then February and March would be your late summer / early autumn. So then in some cases, it kind of fits. So for example, with October, November 1980 and December, January 1980, 81, and then FM 81, they kind of all three fall within that wet season. So what I'm trying to say is that not all of those would actually match. So for example, a wet season may be the 1996 October, November. However, it could have been followed by a dry December, January, February, March. So not all those pairs of months would actually fall in this list. So that's just to break it down. And then another breakdown, just bear with me, is what I realized is when looking at the actual rainfall, it falls differently within the Southwestern Cape itself, because remember, we have the coast, we have the 2 currents that actually contribute to rainfall. Then we also have a large mountainous range, the Cape Fold Mountains, that actually also split the area as well. And that can have orographic effects on the weather. So what I did was I split it into 4 groups. So A, the West Coast, because there's a lot of influence from the Atlantic on the west. And then the greater Cape Town area is in blue. So that's where we currently are. And then the Overberg, so that's also influenced by a lot of what happens in the Southern Ocean, as well as the Agulhas that tracks to that area. And then also the Karoo, which obviously is influenced by mountains. You anticipate a lot of blockage there and not a lot of uplift. So looking at how it relates in terms of mean total rainfall and number of rainy days, obviously in the areas where there's a lot more rainfall days, so for example, in your zone B, the Greater Cape Town, and C, your Overberg, you find that the relationship becomes a bit wonky. It's not as direct as, for example, zone A and zone D, which almost have a direct match up between mean total rainfall and number of rainy days. So what I then did was I analyzed the pair months and looking at each zone and seeing what pair months show significant decreases in rainfall days. So what I've looked at in terms of if you go up north, so looking at the central Karoo area, as well as the West Coast area, you see that a lot of the shortening of rainfall days actually happens in October, November, which you don't necessarily see in zones B and C, which is more your Cape Metropole. It's where the dams are. It's where most of the rain actually matters in terms of dam volumes. But then they have those ones, so the Greater Cape Town as well as the Overberg, they show more decreases in the core summer, so in December, January, as well as all four actually showed consistent decreases in February, March, and they're all significant at a 95% level. So then I looked at what could possibly be the circulation patterns that influence the rain coming towards South Africa. And I looked at a lot more features and mechanisms than geopotential height. However, I'm just using geopotential height here as an example. I also looked at upper wind speeds as well as mean sea level pressure. So with FM, with February, March, it's doing what you kind of expect it to do. So a lot of the cutoff low cyclogenesis, or where it originates from the tip of just east of the tip of South America, which is that blue blob we see on the graph. The December, January isn't as clear cut as that. Yes, it does show a slight low pressure, so it's indicative of cyclogenesis. However, the blue blob at the bottom of South Africa suggests to me that a lot of the tropical air is moving southwards. So that's more indicative of a West Coast trough, or as most people know it, cloud bands or tropical temperate troughs. So this is a cross section at 10 degrees east, so longitude. So if you look at just before you get to South Africa, it's a cross section of the atmosphere at that point. So looking at this, what you see is a red blob at 30 to 40 south, which is what you kind of want to see. Think of the red blob as wind speeds moving towards South Africa, which is what you want. The blue is kind of inhibits the movement of systems into the area. So what you can see is both February and March and December and January encourages storms to track actually to the area. I forgot to mention the wet and dry. So it's basically all your wet composites, the average of all your wet seasons minus all your dry seasons. So it almost hyperbolizes, if you will, what actually happens during wet seasons. So one thing other than circulation patterns we kind of need to take into consideration is the position of the South Atlantic high pressure system. And there was a nice paper by Natalie Burles, which notes about poleward expansion. So as the South Atlantic high pressure system increases poleward, you will have less rainfall in South Africa. But how does that mechanism actually work? So I know you can see the green. So the green section is the only part that was significant when it came to trends in South Atlantic high pressure. So you can imagine that green section actually extending downwards towards the poles and what that would actually mean. So for example, you have your cutoff lows forming at the tip of South America, but then they have to propagate into South Africa. So how would it actually go about doing so when the South Atlantic high pressure system has now expanded and there's this kind of blockage there? And what we've actually seen is that trend has been significant. So then looking at storm counts, so looking at storms in the different bands, so looking at 50-60, so closer to your poles, then 40-50, so mid-latitude, and then 35 to 45S, which is kind of the sweet spot just before South Africa. And what we found is actually that the storms are picking up in the 50 to 60 band. So it's not that the storms are not being generated, it's just that they're not translating towards South Africa. So if you look at the purple, you actually see a decreasing trend. So one other aspect we considered was actually modes of variability. So we try to compare rainfall and storm counts with all kinds of modes of variability. We considered the South Indian and South Atlantic Ocean dipoles. We considered the zonal wave number 3, which is not as common as the others. It's basically just a measure of 3 pressure points in the Southern Ocean. And then we also look at ENSO, El Nino, which did have some kind of links with December, January, but it wasn't significant enough. The most significant one is the one that Mahlalela found out as well, which is your Southern Annular Mode, so SAM. So we looked at two different indices of SAM, so the Marshall Index as well as the Era 5 one, which is the most recent one. And then we compared it to storm proportions. So as you can see, the more negative, generally, it's not a linear relationship, but the more negative SAM becomes, the more you have in the way of storms. So just to conclude, large rainfall events are characteristic of wet seasons, and they have cutoff lows and atmospheric rivers are the dominant rain-bearing systems that there are. Large rainfall events are essential for dam volumes in the driest time of the year, which is also when most of the evaporation happens. The last 2 decades do show more dry years, so you can come up with whatever conclusion you want with that droughts are going to become more prevalent. Drying in the south of the Southwestern Cape in the poor late summer, and the north shows drying in the spring and late summer. So basically, with that, we have a resource, our dams, they'll become a bit more volatile in terms of volumes because of the uncertainty in the rainfall. Circulation patterns track with a lot of the wet season, so a lot of them coincide with what is actually happening in this mid-latitudes and in the Southern Ocean, because that's where most of our rainfall actually derives from. The summer rainfall is linked to a negative SAM, but also other modes of variability. So for example, for February, March, I found a lot of South Atlantic Ocean dipole, but it was, again, not significant enough compared to SAM as well. And then storm track towards South Africa can be linked to prevailing winds and South Atlantic high pressure systems. So looking at how the movement of these rain-bearing systems, but also whether or not there's an actual blockage. And if there is a blockage, it's unlikely that these storms would actually track into the Southwestern Cape, which then results into drier seasons. I think that's me for now.
Thank you so much, Wade. That was really interesting. I definitely learned a lot. I haven't done meteorology stuff since like school, basically. So I was remembering things. Cool, thank you. Does anyone have any questions? You're welcome to raise your hand and unmute or pop them in the chat.
Hi, I don't see why I should raise my hand on my side. Can you hear me?
Perfect, you can talk.
Yes.
Yeah.
Yes. My name is Nkateko here. Yeah, thanks for the presentation, really well presented. I just want to check something. I did miss some of the sections because of my network. However, I just want to check here. You mentioned something very interesting at the end to say that in the last two decades we had fairly dry conditions. However, I want to check in your write up, did you at any point look at the relationship between the rainfall as well as the cyclone activities in the especially in the east coast of the country, because we've had some really intense cyclone activities, which I might believe that they might have also contributed to, in my personal view, I would have thought that they would have contributed to a high rainfall. Did you at any point look at that? Or number two, did you match your rainfall pattern with the the stations which we have in the oceans, like your Marian Island station as well as your Sinai station? Did you match the precipitation and maybe look at the link between those as well as the rainfall seasons? So yeah, that's what I'm mostly interested in understanding, if you ever did look at that. Thank you very much.
Okay. To answer the second part of your question, I didn't look at it, just because I didn't think it would necessarily tell me anything, because, for example, Marian Island is quite small. So, for example, if you have a cutoff low that's moving across Marian Island, it won't necessarily track because they are quasi-stationary. So it's not like they rain all the time. So it's difficult to determine whether or not that would actually link to what's happening in the Southwestern Cape. To answer your question about the East Coast, so Mahlalela did her PhD, which is accessible on Open UCT. She did a lot on the East Coast. So she does note that what we did realize was that some of the cutoff lows we found in the Western Cape actually tracked as far as the Eastern Cape as well. So that was kind of a huge event. But I didn't account for those days within my research. I only accounted for the days that it actually was within my region. But her paper should be able to tell you more about that.
All right. Thanks, Ben.
Sure.
Thanks, Nkateko. Does anybody else have any questions for Wade? I can say in my brain, when you started talking about cutoff lows and rain and stuff, it's just been our lovely rain that we've had for the last few days in Gauteng. So that's all my brain was thinking about in the beginning.
I mean, you could always bring the rain.
Any other questions for Wade? We're all good.
Cool. They can always reach out to me on email if they do have questions.
Cool. Thanks, everybody. And I think Wade's talk, linking to the rainfall and thinking about dam levels and that kind of stuff, kind of links really nicely to our next speaker. So let me just make sure I get the date right, the 6th of March, we will have our next talk, and that will be by Michelle from Grasslands. So she's going to be chatting about expanding woody encroachment and concerns on water yield. So we've been chatting about the rainfall side of it, so now we're going to chat about the plant side of it when it comes to water a little bit. So thank you so much, Wade, and thank you to everybody who joined us. And yeah, this recording will be up on YouTube in the next few days. So yeah, thank you, everybody.
Thank you, Catherine. Bye, everyone.
Bye.